Ladies and gentlemen, this is the seminar of 4ST601 number 6. If you remember, on the previous seminar we calculated complete regression model manually, and after I tried to show you something in Microsoft Excel, and if you remember, we finished in the middle of one example about regression parabola, quadratic regression function. So I hope that you have ready this previous example, as we are in the point where we have calculated parameters for regression line and parameters for quadratic regression function, regression parabola. And we must compare these two models. So make your formulas ready, and we will continue with evaluation of two different models. I must compare the line and the parabola. How can you compare two models? Parabola using three b's, three coefficients. Line using two coefficients. Mr. Hellman said to you that different models, which modeling the same in our situation amount of yield, yes, different models you can compare by adjusted R squared, adjusted version of coefficient of determination, adjusted version of R squared. So please check your formulas and find here the formula for adjusted version of R squared. It's here, yes. I will zoom this document, and R squared adjusted is calculated here. So what is written here? 1 minus, in parentheses, 1 minus R squared, index of determination, the origin one, times the ratio. What is in the numerator? N minus 1. What is N? Number of observation, sample size, yes, N minus 1. In denominator, N minus P, number of observation, minus number of B's, number of coefficients, number of parameters. Constant, linear regression function has constant and slope 2, yes. And parabola, quadratic regression function, has 3, b0, b1, b2, yes. So I can show you, yes, I can show you how can you calculate adjusted version of R squared for parabola, yes, in Excel. Do you remember this formula? You can use print screen, yes, or you can use paper version of formulas. So in Microsoft Excel, here, this is my parabola, yes, this is parabola, and here you can see here R square, yes, and there below you can find adjusted R square, yes, but I know the formula, and I will try for you to calculate this value, yes, by the formula. So I know that there is 1 minus, in parentheses, 1 minus R squared times, in numerator, N minus 1, in denominator, N minus P, yes. How many observations we have? 7, yes. So it's easy. 7 values in one column, yes. So please solve this. Equal sign. 1 minus, in parenthesis, 1 minus original value of r squared, close parenthesis, times, and there is ratio 7 minus 1. This is divided by 7 minus 3. Why 3? Because this is parabola. You are using 3b, yes, 3b's. b0, b1, b2. Okay, parenthesis here. One more parenthesis here. One more parenthesis here. 1 minus. This will be better to use parenthesis here and parenthesis here, yes? Okay, and this is result, yes? Can you see what I wrote here? This formula, yes? And if I use 4 decimals, you can see that I have the same result. So, now you know that 2 different models, line and parabola, can be compared only on the basis of adjusted r squared, because these models using different number of parameters, yes, 3 and 2. So this is the reason why we are using adjusted version of r squared. So this will be used for parabola 80.31%, 0.8031. This is parabola. And we will check regression line. Regression line is here, and summary statistics are here. Adjusted r squared, 0.8363. Parabola has 80, line has 83. So we can expect that regression line explains a little bit more variability of the data. Yes? If you use r square only, yes, you could make a foul, yes. I don't know if here we will do the foul, yes. We have here 86.35, and here in the case of regression parabola we have 86.87. Yes, we will do the foul, yes. This is parabola, yes, and you can see that you have here 86.87. I will copy these values, yes, wait a second. I will copy these values, r square, so this is for parabola, copy and paste, and this is the line, copy and paste, yes. There is parabola and there is line, yes, and I will use this color, yes. Okay, so check this result, yes. Parabola has higher r square, but parabola using 3 coefficients, yes, we must use adjusted r square if we compare different models. And you can see that line has higher r square adjusted, yeah? So this is the reason why line is in this example better. So we characterized the tightness of dependence, yes, by appropriate coefficient. We selected adjusted version of r squared, and now we can calculate by by the best model, yes, the selected model, the amount of yield when 8 kilograms of the fertilizer was used. We selected line, yes, because line was better on the basis of adjusted R squared. So please use Microsoft Excel and calculate, yes, some expectation, our expectation, yes, about the amount of yield when 8 kilograms. So fertilizer is in kilograms, amount of yield is in cubic meters. In cubic meters, so there is the line, yes, there is my line, okay, equal sign, intercept plus slope times 8 kilograms of used fertilizer. And this result is in cubic meters, yes, in cubic meters, yes, meter powered by 3. So I will use format cell superscript, okay. So this is the response, yes, 69.32 cubic meters is your expectation about the amount of yield if you use 8 kilograms of fertilizer. There is given the output from the regression analysis, yes, of the dependence of dependent variable y on the independent variable x. What it means that we have here regression line only, yes, regression analysis, regression line. You can find here variable intercept and the slope, yes, parameter estimates are here, and there is analysis of a variance table, yes, which you could see in the previous examples, yes, from Excel. But in Excel you could find here different words, synonyms, the words with similar meanings, yes. So this is the ANOVA table. There is the table with parameters of estimates, and what can we do? Fill in missing data. What can we fill? Yes? For example, sum of squares. Yes? Sum of squares. And we can interpret results because we have here parameter estimates. Yes, so we can write the line, yes, and we can interpret the results, for example, on the basis of R square or adjusted version of R square, yes. So please check your formulas. Check your formulas. It's necessary to complete these two cells, yes. Sum of squares. There is between group, there is within group, and there is total. And you know that this part is source of variability, yes? For example, you can check this previous example, yes? There is ANOVA table, yes? And you can find here this ANOVA table. So there is regression, residual, and total, yes? So we have here as well between group, yes, is regression, yes, regression. Wait a second. Okay, regression. One more letter. Regression. Okay, within group, according to this ANOVA, regression is residual or error, yes. So I will write here that this is residual or error source of variability, yes. And the total is total. Okay, so we have here total sum of squares. We have here, for example, R square. Check your formulas. Check your formulas. How can you solve R square? R square is a ratio of regression sum of squares and total sum of squares. If you move this total sum of squares here, yes, like multiplication, you will obtain a regression sum of squares. So we will multiply R square and total sum of squares, and the result will be regression sum of squares. Please do this, yes? Do this and calculate this here. So regression sum of squares will be equal to R square, yes, this value times total sum of squares. Okay, and the result is, I will use only two decimals. Result is 20,653.19. Again, you can return to your formulas, yes, and you know that total sum of squares is a sum of regression and error sum of squares. How can you calculate error sum of squares? Difference between total and regression. Total minus regression is equal to error. So please do this, yes? We will do this here in Excel. So there will be equal sign, total sum of squares minus regression sum of squares. Enter, yes, and you have here a result. Because residual sum of squares, error sum of squares is higher than regression sum of squares, you have R square small, 0.48 only, yes? So this model, yes, explains less than 50% of variability of data, yes? So now, at this moment, we don't know if this model is good or not, because we are not able to test this model, yes, by some test of model, for example. Yes, you can see that we have here some information that we will return to this example later. But now we are able to write at least the function of the regression line. We know that y is equal to parameter estimate, intercept, minus 34.67062 plus 9.10211x. Yes? So this is the formula of your regression line. Another example, you are selling CDs, yes? You are selling CDs and you want to sell a lot of CDs and earn a lot of money. So you invest it to advertisement, yes? Because more people know about your CDs, yes? More people buy these CDs. As I think the influence of two different types of advertisement on sales of new CD, we obtain the following data. So we have here variable sales, yes, in thousands Czech crowns, and the costs on advertisement. Advertisement in radio and television, yes, in thousands Czech crowns, and advertisement in press, journals, newspapers, etc. Yes, and we would like to calculate the parameters of regression plane that is describing the dependence of sales on the amount of cost on advertisement in radio and television, variable x1, independent variable x1, and on the amount of costs on advertisement in press, independent variable x2. So we have here two independent variables, two explanatory variables, x1 and x2, yes? This will be regression plane because we have more than one independent or explanatory regression variables, yes? And we will characterize the strength of the dependence, yes? Do you know which coefficient we will use? Which coefficient? For example, r squared or adjusted value of r squared, yes? We can use, so please, you have installed add-in, yes, with regression analysis, so please, there is data leaf, and there we have data analysis, yes, in the right top corner, data analysis. Please select regression, okay, and I will delete this, and I will scroll down. Where is my example about the regression plane? Okay, now I am at home. So, input y range, yes, I would like to explain my sales, yes, sales, on the basis of costs, yes, on advertisement in radio and television and in press. So I will have one dependent variable and two independent explanatory variables. So please select the columns, yes, select the columns, input y range here and input x range here. Can you see I did not selected the labels? I did not selected the labels, so I must unselect labels. I selected only the numbers, yes? This is very important. And that's all, yes? Click on OK and you will see results. So I will use only 4 decimals here in summary statistics and 2 decimals in other statistics. So please wait a second. Okay, summary statistics ready. I will delete what is not necessary for us. Okay, here I will use only 2 decimals here and 2 decimals here. And what was our duty? Calculate the parameters of regression plane, yes? So I will write the function of the regression plane, yes? So y is equal to intercept 123.7 plus 12.64 x1, the first variable, radio and television, yes, plus 18.86 x2, press, yes, the journals and newspapers. Okay, so this is the function, yes, this is the model of the regression plane with two independent variables. And there was written, characterize the strength of the dependence, because this is only my model, yes, my only one model. I don't have any other model for the comparison. I can use classical R square, yes, classical statistic R square index of determination 0.8324. This coefficient says that we explained more than 83% of variability of the data, yes? So probably this model is good, yes? We don't know because we don't know any tests, statistical tests for evaluation of this model. Yes, this will be the topic of later seminars. Yes, but we can interpret at least the value of this coefficient. Yes, and the size of the dependence. I can continue what is written here. What average increase of sales can be expected according to this model when the costs on advertisement in press increase by 5,000 Czech crowns while the costs on advertisement in radio and television stay constant? It's absolutely necessary to know that press is variable x2, yes, and increasing is 5,000 Czech crowns, but this is in thousands, yes, so the result is 5 times the coefficient of x2, variable x2, yes, so please use your model, yes, use your model here, and the result is 5 times this coefficient, because the costs on advertisement in radio and television are constant, yes, doesn't change. So result is 94.29, but we know that variable y, sales, your sales are in thousands Czech crowns, yes, thousands Czech crowns. So result is 94,290 Czech crowns, yes. So you will invest more money, yes, on advertisement in press. You will use another 5,000 Czech crowns, and you can expect that you will sell more CDs, yes, in amount of 94,290 Czech crowns, yes, 5 times this regression coefficient. And finally, we will calculate expectation about the sales, calculate sales when they're spent on advertisement in radio and television, 40,000 Czech crowns, and on advertisement in press, 35,000 Czech crowns. Radio and television, variable x1, press, variable x2. This is in thousands, so 40 times first coefficient, 35 times second coefficient. Result is in thousands because sales are in thousands, yes? Okay, you can see sales in 1,000 Czech crowns. So here I will use my regression model. Equal sign, intercept plus 40,000, yes, 40 times this coefficient plus 35,000, yes, 35,000 on press. So 35 times this variable, this coefficient. Enter, and this must be interpreted in thousands, yes. So what is it in thousands? 1,289,430 Czech crowns, yes. So this is the response. This is the response of C. Yes. So this is B and this is C. So if you invest 40,000 on advertisement in radio and television and 35,000 on advertisement in press, you can expect that you will earn a little bit more than 1.25 million Czech crowns. Okay, we can move to another types of examples, another lesson, yes? Time series analysis in descriptive way only, yes? Descriptive analysis of time series. We would like to calculate elementary characteristics. We can call these elementary characteristics also the measures of dynamics. Yes, measures of dynamics of the time series gas production. This is annual time series, very old, as you can see, from year 1980 to 1985. So we have here 1, 2, 3, 4, 5, 6. Only 6 observations. Gas production measured in cubic meters. Yes, there we have the data set. Yes, original table is written here, and for your purposes and for your comfort, I already transposed the values, observations to columns. Yes, I hope that you are able to transpose data set. Yes, you can see it's not difficult if you take these two lines, these two rows, yes, and use combination of keyboard Control and C, yes, copy. You can click, for example, here, and there you have paste button. Yes, on the home leaf you have paste button with this arrow. Paste button, yes, with this arrow, and there is a lot of options how to paste it, and we will find transpose. This one, yes, transpose. Okay, and now you have here transpose the data set, yes, two columns, year and production in cubic meters. Yes, you can see it's not difficult. Okay, so we will calculate the elementary characteristics, yes, elementary characteristics of this time series. If you check the formulas, you can see that the descriptive time series analysis is here. We can start with the first differences, delta. Yes, delta in time t. It's a simple difference between the value in time t and value in time t minus 1, so previous value of observation. Yes, result can be called absolute differences or just differences, delta in time t. Yes, so we will see that it's very, very easy. We cannot compute the value here because we don't have observation of production in year 1979. Yes, so we must start here, and the result is value in year 1981 minus production in year 1980. Yes, we lost one observation. Yes, we lost one observation, and the differences can be positive or negative. Yes, positive or negative. You can see that we have positive differences every time. Between year 1982 and 1993, yes, we produced more gas, more by 102 cubic meters. Yes, between year 1984 and 1985, yes, we produced more gas by 39 cubic meters. If this value is negative, is decreasing, yes, between year absolute decreasing. First differences, yes. What is a growth coefficient? It's a ratio, yes. Growth coefficient is a ratio. You can check your formulas, and in your formulas you can find this k in time t, yes. and you can see its ratio observation in time t divided by observation in time t minus 1. Yes? What is it? Ratio, yes, of value in year, I don't know, 1981 divided by observation in year 1980. Yes, so we will calculate these ratios here in Excel again. Yes, it's not possible to calculate value here because you can see that we don't have observation in year 1979. So again, we will lose one observation. Yes, one observation is lost. There is equal sign, yes, and it's this value divided by this value. This is very important, be careful, yes. Very often mistake done by student is to calculate coefficients from these values. No, yes, this is the first difference. There we have growth coefficients. We must calculate results from original data, production of gas, yes. Okay, so this simple ratio, and what is the result? Result is relative number. Result is relative number. What is it, relative number? Yes, number around 1. If this number is higher than 1, result is increasing. If the number is below 1, result is decreasing. You can see everything is above 1, so you are able to interpret this value in percent. Yes, 1.06. It means that between year 1980 and 1981, production of gas increased by 6%. Between year 81 and 82, production of gas increased by 2.2%. Yes, the highest, the largest increasing, yes, of the production of gas was between year 1982 and 1983, 102 cubic meters of gas. In relative expression, this is 7.3%. Yes. 5.1% increasing between year 1983 and 84, and 2.5% is the last value. How can you imagine the decreasing value? 0 point something, yes? 0.90. 0.90. What is it? Decreasing by 10%. Yes? 0.90 decreasing. 0.98 decreasing by 2%, yes, etc., etc. So first difference is growth coefficient, and we can continue mean first difference. Mean first difference. Check your formulas. In the formula sheet, you will find this delta with stripe, yes? Delta with stripe is equal to something. I will use this last part. Observation, the last one, yes? And observation minus first observation, y1, yes? Divided by number of observation minus 1. We have 6 values. So denominator is 6 minus 1, and the numerator last observation minus first observation. Yes? So we can do this, and result is mean first difference. Mean first difference. So you can calculate here equal sign. I will open parenthesis, and there is difference. Last observation minus first observation, yes, divided by, and there is 6 minus 1. Again, it's very important, yes, to take original data, yes. Don't use differences or growth coefficients, yes. Last observation minus first observation divided by n minus 1, 6 minus 1. Yes, and result is mean first difference, and mean first difference is positive. You can see positive value, and there is written interpretation. It means how many more gas is produced each year. Yes, every year you produced more gas, in average more by 64.8 cubic meters. Yes, so this is average increasing every year. Yes, calculated from the original data set. And the same can be calculated in relative expression. Relative expression, mean growth coefficient. Yes, so check your formulas and find here K with stripe. K with stripe, yes? So we will check the formulas and we will find K with stripe. We will use this last part. You can see that there is a root, yes? N minus 1 root from the ratio last observation yn divided by first observation y1, yes? And because we have 6 observations, so there is 6 minus 1 root, yes? How can you calculate this root? Using power function, yes? We use hat, and we will use power by 1 divided by 5, yes? Because 6 minus 1 is 5, so it will be this ratio powered by 1 divided by 5. Okay, so we can compute this. There will be calculated equal sign, yes? You can open parenthesis and please calculate the ratio last observation divided by first observation, yes? So this is the ratio. Now, please use power function, yes? Again, power function, you can find on the case 6 English keyboard, yes? And shift and 6, yes, and you will see hat. So please use this power function. English keyboard. Yes, there is a hat, yes, and it's powered by 1 divided by 5, yes. Why 5? Because the root is n minus 1, 6 minus 1, result is 5, yes? Okay, so calculate this relative coefficient. Enter 1.046. It's higher above 1, yes? And what it means if this value is above 1? It's increasing, relative increasing. You produced more gas, yes, every year in average by 4.6%, yes? So this is increasing time series. Every year you produced more gas by 64.8 cubic meters, and in relative expression it's 4.6% increase, yes? Every year average increase by 4.6%. Okay, and finally we can calculate arithmetical mean of this flow time series, yes? Arithmetical mean of this flow time series. So I will add here the labels, yes? This is my observation y1, yes? Okay, y1 is here, y2 is here, y3, y4, y5, and y6, yes? So now I will use this table on the right side, yes, observation in year 1980 to 1985, and there is my production of gas. Yes. This average is very simple because it's classical arithmetical mean summation of 6 values divided by number 6. Yes, so there will be equal sign sum. Yes, sum of all these values, close the parenthesis, divided by and we can use function count. Yes, count returns the count of values. I know that I have here 6 observations. Yes, but we can write here count function. You can see returns counts the number of cells in a range that contain numbers. Yes, so count function, I will select 6 values. Yes, close the parenthesis, and this will be divided by 6. Okay, so this is average. Yes, this is calculated average production of gas in cubic meters, 1,453 cubic meters of gas. But now I will use the other mean with weights. Yes, with weights. So what I need? Observations. Yes, observations. Y1, Y2, etc. The last will be 6th observation, Yn. Yes, number of days of the particular year. So I need another column, DE. Yes, DE. Okay, production, copy format, DE. Okay, number of days. I wrote for you number of days here. Yes, 366 days. Yes, has the year 1980. 365 days. Yes, has year 1981, etc., etc. So these weights, yes, number of days, I will write here 365, 365, 1984, 366, and this one 365. Okay, so number of days, I will use copy format. Okay, yes. And now, according to this formula, yes, first observation plus second observation divided by 2. This is weighted moving average, yes, with the length 2. Moving average of the length 2, because there is a summation of 2 neighborhood values divided by 2, weighted by number of days, yes. And you can see the last weight is dn-1. So we will not use the last value of days, the last value of the number of days, yes, in the column. In denominator is summation of days, yes, d1, d2 plus dn-1. So again, in denominator, the last observation is not included, yes. So I will start with calculation, yes. Equal sign, I will open parenthesis, and first observation plus second observation, close the parenthesis, divided by 2, yes. I will use another one parenthesis here and another one parenthesis here, and this is weighted by number of days, yes. can you see this first part? y1 plus y2 divided by 2, weighted by number of days. And we will move, yes, we will move through all the time series. So please use enter and calculate everything what is possible. The last possible calculation is presented here because there is y n minus 1 plus yn, fifth observation plus sixth observation divided by 2, weighted by d n minus 1. Yes, we will not use the last value. Yes, so we have here these parts, yes, in a nominator. So now summation of these values divided by number of days from first observation to fifth observation, yes. So there will be calculated the mean, equal sign, sum, yes, summation of these values, okay, divided by, I will open the parenthesis, this value plus this value plus this value plus this value plus this value, and this is the end, yes. The last number of days, dn, is not included, yes. Okay, press enter and we can compare this result with this result, yes. Okay, so enter, and you can see there is a difference 1 cubic meter, yes, 1 cubic meter, 1 cubic meter of gas, yes. So this is a difference. It's very small difference, yes, but because this is annual time series, yes, and one day, yes, probably one working day, yes, is not such a big difference, yes, if you use the classical mean and this weighted version of the mean, yes, but if you calculate this, for example, on monthly published time series, yes, it's necessary to use this weighted version because February has, for example, 28 days, yes, January has 31 days, yes, and the number of working days, yes, is very often a significant factor, yes, which can influence the mean, yes. So in the case of annual time series, it's voluntary, yes, to use because you can see that we have almost a similar result, but in monthly, yes, quarterly or monthly published time series, it's necessary to use this one, yes. Do you remember when I said that if you analyze the monthly published time series, it's good to use weighted mean for the calculation of average? For example, here the average number of workers in this company. The table below shows the number of seasonal employees, yes, temporary workers in the car factory. The number are valid on the first day of the particular month, yes, and you would like to calculate the average number of these workers. Monthly published time series data available on the beginning of the particular month, yes. We would like to calculate the mean, the average, but you know, I said already this information to you, yes, that for example February, yes, February has different number of days, yes, and here if we use classical mean, classical average, yes, you can try it, equal sign, average, yes, equal sign, average, and average number from these values, yes, this is wrong. We must use this formula here, yes, which we already used. January plus February, yes, divided by 2, weighted by number of days in January, plus February plus March, divided by 2, weighted by number of days in February, yes, etc., etc. So please, we can write here number of days, DE, yes, another variable, number of days, yes, number of days. I will use formatting here, yes. We know that 31 days, yes, has January. 28 days, yes, has normal February. 31 days has March, January, February, March, April. 30, May, 31, June, 30. During summer, yes, summer holiday, June and July and August, yes, we have 31 and 31, yes. September 30, October 31, November 30, and December 31, yes. So there we have the days, yes. And now, according to formula, yes, which was written in your formula sheets, yes, we will use moving average of the length 2, yes, the sum of two neighborhood values divided by 2, weighted by D1, D2, D3, D4 until Dn-1. So December will not be used, yes, we will not use the December. Okay, so the partial calculations, yes. Please watch this pointer. I will open another parenthesis. So open. First observation plus second observation, close, divided by 2, yes, close, and times weighted by number of days in January, yes, and we will calculate 11 partial values. Why 11 only? Because if you check this last formula, yes, you could see that there is observation yn-1, yn, yes, divided by 2, it's weighted by number of days, Dn-1, yes, according to your formulas. And now we will calculate the summation, the sum of these values, divided by number of days from January to November, yes. December is not included. So, enter. I will calculate here equal sign sum, yes, summation of these partial values, yes, close, divided by sum, yes, summation of number of days from January to November, yes. If you check your formulas, you can see that there is D1, D2, D3, and the last is Dn-1, yes, it's not the last value, yes, and again here you can see yn-1 and yn, yes, and the last weight here is Dn-1. Okay, so you can press enter and you can compare the results, yes? More than one worker, yes? More than one worker is difference if you use this wrong approach or correct approach, yes? And now you can imagine that we don't have here workers as the persons, but billions of dollars, yes? And there is difference as $1 billion, yes, or more than 1 billion. So it's very important, yes. In the case of quarterly, monthly published time series, yes, it's necessary to use this weighted version. For example, analyzing of time series when you are using only working days, yes, working days. It's also important because some months, because for example of state holidays, yes, has different number of working days than another month, yes. So this general formula is very, very useful. Okay, see the sheet 2. You have here another data set, another data sheet, which is published by the Czech Statistical Office. Yes, there are vital statistics of the Czech Republic from year 1992 to 2016. Absolute monthly figures published by Czech Statistical Office. It's official document. Yes, download it from the internet, from official websites of Czech Statistical Office. We will use monthly published data about the net migration in the Czech Republic between year 2015 and 2016. Yes, for your comfort, yes, for your personal comfort, I copied these values, yes, empirical data here. 2015 January. Yes, and the last observation here, 2016 December. Yes, the values. Yes, the values are in persons, number of inhabitants. Yes, persons. We can check this data sheet at home. You will have a lot of time. Yes, to check this data sheet, vital statistics of the Czech Republic, absolute monthly figures. English translation, yes, you have every time on the second line. Yes, the first name is in Czech language, in English language is on the second position. On the right side, yes, there you have period, yes, in English. Net migration is this column, yes, and we can scroll down because you can see that from the beginning we are starting with annual information, annual numbers, yes. If you scroll down, you can see that period, yes, period is published, transformed to quarters, yes. And if you scroll down, you will see that you have available also monthly published data. Yes, there we are starting with monthly published data. Net migration is still here. So I'm scrolling down, and two last years, yes, which are here in this data sheet, old historical data sheet. Yes, if you want, you can download new one from the websites. Yes, so there you have yellow values, and these yellow values I used. Yes, January 2015. Yes, so this column, and from January 2016, yes, to January 2016 to December 2016. Yes, okay. So this is your data sheet, and you have copied this data here. we will transform this time series to quarterly time series. Yes, of course. I showed you this data sheet. You can check quarterly published part, yes, and copy these values. But we know that these data, yes, are published in persons. Yes, we have here number of inhabitants, and because first quarter of the particular year is January, February, and March. Yes. If we calculate sum of three values, January, February, and March, we will obtain first quarter. Yes. Second quarter is April, May, and June. Yes. Because this observation, yes, is number of people. Yes. So we can calculate simple summation. Yes, and we will obtain quarterly data. So we can do this. Yes. So here will be calculated equal sign. So this value plus this value plus this value is the first quarter of year 2015. Yes, equal sign April plus May plus June. Yes, is second quarter. Equal sign July plus August plus September, yes, is the third quarter, and here equal sign October plus November plus December, yes. Okay, and now we can continue year 2016, equal sign January plus February plus March, enter. Equal sign April plus May plus June, enter. Equal sign July plus August plus September, and here October plus November plus December. Yes, I will use the same formatting, copy format. Okay, so this is quarterly published time series. Yeah? So I transformed this monthly time series to quarterly data. Okay, and you talked with Mr. Hellman about the smoothing time series by moving averages. Yes? What is it, moving average? You could see the first moving average in two previous examples. There we used moving average with length 2 because we calculated summation of y1 and y2 divided by 2. It was moving average of the length 2. Yes? Weighted, because there was multiplication multiplied by number of days. Yes. There we have quarterly published time series. We will smooth quarterly time series by appropriate moving average, which length is necessary for quarterly published data. Length 4, because we have 4 quarters in the particular year. Yes. If you use smoothing on monthly published data, it's necessary to use moving average with length 12. Yes. So we will use length 4. Okay. Write down on the paper only the first calculated first four, yes, first 4 values of these averages. Write down the paper only the first 4. It will be enough. Yes, 4 calculated values of these averages. Okay, so we can start. Yes, equal sign, open parenthesis. And now, what is it moving average with the length 4? First observation plus second observation plus third observation plus fourth observation, close the parenthesis, divided by 4. Yes? So this is moving average. So you can see it's easy. We'll take 4 values, yes, sum of 4 values, and we will divide the result by 4. And we will move. It's moving average, so we must move through the time series. So I will calculate this, and I will continue with another possible value, yes. So we can continue. I will use formatting, yes, and I will calculate these values here. So equal sign, I will open the parenthesis. Second quarter plus third quarter plus fourth quarter plus first quarter from the new year, yes, year 2016. Close the parenthesis, divided by 4, yes, and you can continue. Equal sign, open parenthesis, yes. This is already the third possible value. So third quarter, fourth quarter, first quarter from the new year, second quarter from the new year. Yes, we are moving through the time series. So continue. This value plus this value plus this value plus this value, close, divided by 4. And I will continue. Equal sign, open the parenthesis. Fourth quarter plus first quarter plus second quarter plus third quarter, yes, divided by 4. And equal sign, open parenthesis. First quarter plus second quarter plus third quarter plus fourth quarter, close, divided by 4. Enter. Okay. We want to calculate moving averages with the length 4, yes, on this quarterly published time series. If we calculate some result, we must have the place, the cell, yes, the cell where it's possible to write the result, yes. We started with the calculation of moving average, and this result, 3994.3, must be placed here, where is the black line, yes. But I don't have the cell. Yes. I want to write the result in the middle. This length 4, yes, is odd, yes. If this length will be even, 3, 5, 7, even, yes, it will be very easy, because if you calculate moving average of the length 5, yes, of the length 5, you have 1, 2, 3, 4, 5. You have 5 values, summation of 5 values, divided by 5, and the result is written here, in the middle, yes? Even length, but we have odd. 2, 4, 6, 8, etc. 4, yes? So we cannot write the result here in the middle. So we must continue. This is not the result, yes? This is not the final result. Write down on the paper only the first 4 calculated averages, values. If you select correct answer, these 4 values, it's wrong, because this is not the end, yes? You must continue, and you must calculate equal sign sum of this value and this value, close, divided by 2. You must calculate the mean, the average from neighborhood values, because the result must be placed here in the middle. Yes? So this will be first one calculated value, yes, of these averages. So we will do this. Enter, and we can continue. Equal sign, open the parenthesis. This value plus this value, close, divided by 2. Yes? So we calculated moving averages with the length 4, but because length 4 is not even, is odd, we had to continue, yes, with this modification. And you can see that from 8 values, 8 quarterly published values, we are able to calculate, write down on the paper, only first 4 values. No more, yes, because we don't have more data. We don't have more data. You can see, yes, enter, equal sign, open parenthesis. This value plus this value, close, divide by 2, and equal sign, open parenthesis. This value plus this value, close, divide by 2. And there you have the final results. Yes, final results. I will use only 1 decimal. Yes, because we have here persons, people. Yes, so these last 4 values, yes, are 4 calculated moving averages. 4 calculated moving averages of the length 4. Yes, it's a little bit complicated. Yes, but most of times, yes, most of times you have odd length. Yes, not even. Even will be easy, but yes, working days, Monday, Tuesday, Wednesday, Thursday, Friday, no weekend, and new working week, Monday, Tuesday, Wednesday, Thursday, Friday, 5 days, yes? So we have 5 days, 5 days, 5 days, 5 days. So we could use, yes, we could use moving average. Moving averages is length 5. Yes, and result will be written on the median position, yes, to the middle, yes, on the 3rd position. So this result will be complete, yes, if you calculate summation of 5 values divided by 5, result will be written in the middle, and that's all, yes. But now we had to continue. Do you know what is a base index and the chain index? Base and chain indices, yes? Again, another very easy, simple method, yes, used for interpretation of the development of the time series. There is the line with 2 formulas. Yes, the first ratio, there is written yt divided by y1, and there is yt divided by yt minus 1, yes. So observation, yes, on the line, yes, in the time t, divided by previous value, yes, previous value. So this is chain, yes, the series, calculation of series of chain indices, as the chain. And here, maybe it will be better to write here instead of y1, y base. Because I can say to you that you will use another base, not the first observation, yes? Observation t, yes, in the time t, divided by first value, yes, first value. But I can say to you, use another observation, another base, yes? Not, for example, Monday, but Wednesday. Use the base Wednesday. Why? Because I want it, yes? I want the base set on Wednesday, yes? Czech Statistical Office, yes? If Czech Statistical Office calculate base indices, yes? The officers using the base set in year 2015. 2015, yes, is currently the base period, yes, and the development of the gross domestic product, consumer price indices, average wages, yes, etc. This development is compared with basic period set in year 2015, yes. So why not? Why cannot we use different base? Yes, of course. I will show to you base indices with base on the first set on first observation, but I will show you example where I require another base. Yes. So here in this data sheet we can use monthly published data about marriages and divorces in the Czech Republic in year 2016, published by Czech Statistical Office. Yes, you can find these data, yes, also in data sheet which I downloaded for you. So we have here monthly published time series, calculate base indices and chain indices. The base observation set on June. This is my requirement, yes. So we will calculate 3 series for marriages, 3 series for divorces, base indices with different base and chain indices. Yes, you will see it's very, very easy because you are computing only the ratios. Yes, so please. Here we will start. So base, January, marriages. Yes, base January marriages. Now base June. Yeah, this is my requirement. Base June marriages, yes, and finally chain marriages, yes. So there, chain marriages. Okay, and another 3 values, yes, another 3 columns. Base, January, divorces. Okay, another column. I hope that I will have enough space. Base, June, divorces. Okay, and the last column, chain, divorces. Yes. Okay, so we have 6 columns, yes, and we can start. Base, January marriages, yes. So we can calculate here equal sign, yes, base January marriages, yes, divided by the base marriages, but you will use function 4. Function 4, you will log the base, yes, and you will see that the result is 1.000 because the base index, yes, calculated on the basis of base must be 1, yes, and other, yes, development, other indices, yes, are comparised with the base. So if you click enter and if you increase decimals, so please increase decimals, 3 values, yes, you can see that there is value 1.000, and if you calculate, yes, if you calculate the development to the end, you have here indices, yes. This value 1.40, 1.400, yes, means that marriages, yes, in March are higher by 40% in comparison with January, yes. In January there is cold in the Czech Republic, yes, and almost nobody, yes, want to have a wedding, yes. So this is the reason why this number is very small. You can see, yes, that this is very difficult to interpret. 849% increase of marriages in July in comparison with January, yes. In June, July, August, yes, September, nice hot September, yes. Most of people want to have a wedding during summer. Yes, so this is the reason why these indices are much higher, yes, than in winter. Because of this very large values, yes, I decided that I will use June like the base, yes, and interpretation of values, yes, will be compared with June. So equal sign marriages, yes, in January divided by marriages in June, this one, yes, June. And again, the base is the base. So function 4, you must lock the cell, yes, you must lock the cell. Okay, so enter. Again, you can use only 3 decimals, and you can calculate these indices to the end. Yes, everything is all right. 1.000, yes, is in case of June, and everything else, yes, is compared with the June, yes. So for example, this value in September. In September, we observed less marriages than in June, less by 7.9%. Less by 7.9%. It's below 1, yes, it's decrease. In August, yes, we observed less marriages than in June, less by 17.2%, 17.2, yes. So here everything is compared with January. Here everything is compared with June. And chain indices will be calculated here. Equal sign this value divided by this value. It's the same like coefficient of growth. Coefficient of growth, yes? Do you remember growth coefficient? We lost one observation, yes? We lost one observation at the beginning because we are comparing two neighborhood values, yes? Between January and February, number of marriages increased by 25.5%. Between February and March, number of marriages increased by 11.6%. Between March and April, number of marriages increased by 300 and almost 5%. 304.9%. Yeah? Very significant increasing, etc. As you can see, between March and April, increase from 1,000 to 4,000 marriages. Yes, it's a very significant increase. So, base indices, chain indices. Yes, and the same you can do with divorces. Okay, this is the end of the 6th seminar. We dealt with other parts, other regression models. Yes, we continued with time series and with indices. So that's all for today. I hope that everything was clear, and I will see you next week on the next 7th seminar. So have a nice day and bye bye.